I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm an undergraduate student studying material science and engineering here at the University of Utah. And I'm joined, as always, by Dr. Taylor Sparks, an associate professor here as well. Today, in light of the holiday seasons, we're going to be talking a little bit about consumption and the challenges of recycling in material science.
And here I thought we were going to do an episode on wasting all sorts of materials, and you and your good-heartedness directed it towards recycling. Good move.
It was something I've come to realize in more recent years that during the holiday seasons, people bring lots of food, there's lots of packaging, and you have to wonder where it all goes at the end. And if I see that in my family, it must be present in other families as well.
I'll say I didn't notice it as much until I had my own family with kids, and now I'm the person who takes the garbage out, and I see that those weeks after Christmas, the bin is overflowing, totally full of wrapping paper and garbage. So if I'm doing that, probably other people are. We're generating a bunch of crap around Christmas time.
Mm-hmm. And that presents a lot of challenges, both from engineering those materials to either be compatible with landfills or be in such a state that they can decompose or be recycled, and actually the challenge of actually recycling those materials as well.
So let's dig into some of the numbers. How much are we recycling? How much are we not recycling? How much waste are we talking about?
Well, this brings up significantly, this time of the year brings up the most amount of waste compared to any others. In the UK alone, they use about 227,000 miles of wrapping paper, which is about 365,321 kilometers. Now, what was kind of interesting is when I was doing this article, I thought that being in the UK, they would have used kilometers, but apparently they use miles over there.
They use miles per gallon instead of miles per liter too.
Huh.
I just want to point out that distance, that amount of wrapping paper, the fact that they're measuring it in miles is bonkers, but that's enough to go to the moon. We wrap our way to the moon every year. This is a crazy amount of paper that we're using every year.
And that's only in the UK. Imagine the rest of Europe, the United States. These are large populations that are all typically celebrating these holidays. On top of that, we use about 4,500 tons of tinfoil to wrap our food and our dishes. And on top of that, think about all of the gifts that people give. Now, it's hard to get as many stats on this, but, for children at least, toys are a $22 billion industry, and that's pretty huge. And you can think about all of the products that are created and given as gifts during this time. And it's kind of hard to measure directly where that goes into waste, but over time it definitely does. And when you see that 90% of these toys contain plastic, most of which, these plastics aren't recyclable, that represents a huge problem for long-term waste. And so when every year we have a spike in consumption of these materials.
I don't ever think about recycling old toys. When I recycle, it's things like paper and cardboard and tinfoil and stuff like that. I never think about that old Barbie doll that the kids don't want anymore. I just kind of take it to Savers and hope that somebody wants to use it there. I guess that's recycling, but I certainly don't bin it for recycling.
Right.
So actually, if you look up municipalities, they see that during the Christmas season, New York, for example, sees about 25% more material that gets put out for recycling. So some people are doing this. I wonder if they're doing it correctly, because I know a lot of the wrapping paper can't be recycled for reasons that we're going to get into in this episode. But at least maybe people are thinking about recycling with all this additional waste that's being generated.
Mm-hmm. In line with this, the UK sees about 30% more waste that gets produced. But the other thing to think about is that now we're seeing a lot of more sophisticated toys and gadgets that are being consumed during Christmas, whereas, a couple decades ago, toys and gifts were a lot simpler. They might have only be comprised of one material or just be very simple from a mechanical or technical standpoint.
My wife is a big fan of very simple wood blocks. We have young kids, right? And so building blocks and the log cabin, things like that. There are these things are going to last a very long time, but as gifts become more technologically, advanced, like I don't think they last as long. In fact, there's this idea, I don't know if it's a conspiracy theory or not, but certainly a lot of people think that companies design products not just around Christmas, but all the time to fail after a short period of time, a couple years, so that you have to buy the new model. I actually did some snooping on this, and I couldn't find any evidence of that. It may well be true, but I didn't find any hard evidence. But it's not like they're designed for crazy longevity either. If you've got a cell phone that's 3 years old, that's starting to feel like a dinosaur, and that's crazy because 3 years is not that old.
Yeah. When I interned at a company, I was on the product design team, and the thing that they had told me was that, you kind of want to find the balance where they want to make a product that's going to outlast their competitors and provide value to the consumer, but if it lasts forever, then they can't sell any more of them.
Yeah.
So it's kind of a dilemma from a financial standpoint where you want to think about the environment and creating materials and products that are going to last, but there's also the economics of that as well. Speaking of these really complex toys, even for kids, they're getting much more sophisticated, like older. As you get older, you start to want, especially today, all the new fancy gadgets. But even kids, my cousin's daughter got this crazy thing where it comes as an egg, and you have to do all these things to it as an egg and keep it warm and rub it or whatever, and then it hatches and this creature emerges and you have to feed it, and it's crazy. I can't imagine how many different components are within this thing, and if you throw that away, how many batteries, how much metal, how many different electronic components and plastics are going to be in there.
Batteries are interesting. One of the graduate students in my research group, Danny Beatty, she did her research an REU last summer, I think it was, at MIT, and her project over the summer was looking at lithium-ion batteries and looking specifically at cobalt. They use cobalt in the cathode, and basically it's critical. We try and make batteries with less cobalt, and that's a big effort right now, but right now they're still using a lot of it. And as we make more vehicles electrified, the Cybertruck coming out this week, and there's lots of talk about electrification of vehicles, there are different scenarios that predict how many batteries we're going to need and how much cobalt we will need to make those batteries. And essentially, in the not that far future, we will not have enough cobalt to make the batteries we need, was the result of her study. I'll put a link to it in the notes. Unless we start either opening new mines, which there's some ability to do that, or recycling batteries. We're going to have to start recycling lithium-ion batteries, which is something that we just do not do right now. We have essentially 0% lithium-ion battery recycling right now. So what else? When it talks about recycling, what are we recycling? What are we doing a good job with, Andrew?
Yeah, so looking at the U.S. broadly, within a given year, at least the last reported one that I have data on was in 2017, we generated 267.8 million tons of solid waste. This breaks down into 139.5 million tons that enter a landfill. So this is just trash that cannot be recycled, reused in some sense, and just goes into the ground. 34 million tons of this is combustible, and so it's burned for energy. 27 million goes into compost, and 67 million tons go into recycling. And I have a little graph here showing how these numbers have changed since 1960 up until 2 years ago. And what's kind of interesting is when you go from 1960 to about the year 2000, you see a dramatic increase in virtually everything, recycling
basically,
especially.
We didn't see any recycling or composting or anything before 1960. We were just massive consumerism, and we didn't care about it. Just all went to the landfill. But in those years between 60 and the 90s, maybe 80s, we started to wake up and start do this more and more. And you're saying around the 2000s, what happens?
A lot of it flatlines. We don't really see a lot of change in terms of the amount that we're recycling, the amount that's going to compost or landfills. It's kind of flatlined, and that kind of presents the new challenge of how do we, bring that even further. And that kind of stems into some of the challenges that are facing recycling at the moment.
Right. So for the last 2 decades, there's been essentially no change. We're sending the same amount of material to the landfill, combustion, composting, and recycling with very little changes. Why do we do things the way that we do right now? Well, right now in the United States, we do what's called single-stream recycling. What that means is that if you have a garbage, for recycling, a garbage can, it's probably going to put your glass bottles, your cardboard, your paper, metals, they're all going to go in one place. And when you send it off to the municipal area that does the recycling, they're going to try and do the sorting there. But the individuals don't do the sorting. And that's not how they do it everywhere. For example, Even in Salt Lake where I'm at here, we don't put glass in our recycling. Glass bins, you have to go and turn those in elsewhere, right? They'll come and pick up the rest of the stuff, but glass you have to turn in somewhere else. In the town of Kamikatsu in Japan, they take this to a whole new level. Now, they have this ambitious goal. It's a small town of 1,500 people. But by 2020, they want to be zero waste. And to do that, they have to recycle everything. And they have 45 different buckets for collecting waste. It's insane. Can you imagine doing that? Taking your garbage and now carrying your garbage bags to this place and splitting up into 45 different bags. But that's what it takes to completely recycle. That's on the extreme, and that's probably not something that's going to be adopted.
In any case, the big difference here between the U.S. and a lot of the other parts of the world is where the onus is on sorting these materials. In a lot of other parts of the world, you have, it's on the consumer themselves to sort their waste at the end, put it in the appropriate bins or, appropriate collection areas, such that it can be later processed. Whereas in the U.S., under our single-stream system, it really is the onus is on those recycling companies themselves. And for the most part, this sorting is done by hand. So there's a conveyor belt of scrap that goes through, and people have to pick out.
Literally pick out, that's cardboard, that looks like aluminum, and it's just as fast as you can do it to make this economical.
Right.
I imagine with this relying on these places to sort it, you're going to get impurities. What sort of numbers are we talking about?
Yeah, so when you're recycling, one of the big things you want to worry about is contamination in the end product. And under single stream, the end product contamination is usually about 15% compared to only 2% under dual stream in Ann Arbor, Michigan. And so this is due to single stream causing a lot of commingling of different types of recyclables and different qualities. So you can have lots of you can have paper that's copy paper, and you can have newspaper or paper used in packaging, and these are vastly different qualities of paper.
Yeah,
and when it
you
comes
can't
to
just put those all together and recycle them. You have to separate those.
Yeah, and so one of the ways that they can do this is they can downcycle things. And so if they know this is going to be of lower quality or they're not going to be able to get it, they can say, okay, well, instead of trying to recycle this into copy paper, which needs to be high quality,
maybe they burn it, or they
make a lower quality product.
They shred it and make something else. Yeah.
But one of the idea behind single stream in the first place was that it would encourage more people to recycle by taking the onus and the difficulty off of them. If they don't have to go through the trouble of sorting things, then the idea is that this will actually increase the amount of materials that end up being recycled.
Well, I can say that it's easier for me because I have one garbage bin. It's easier to put it all there. If I had to have 5 or 6 different bins and separate it, it would be I think people would be less likely to do it. One way that the companies have tried to make this a little bit easier to separate things is, at least with plastics, most plastic devices, pick up the nearest thing that's made out of plastic. Water bottles are good examples. If you flip it upside down, there's a very good chance that you'll see the little recycle symbol with a number in the center of it. And what that's telling you is that all the bottles that have the same number should be put together because they're made of the same thing, and they're basically collecting them. So those might be your PET bottles separate from your polyethylene bottles, right? They're separating those for you. That makes it a little bit easier to separate things that otherwise look quite similar.
Okay, so we talked a little bit about paper. We talked a little bit about plastic, at least on a basic level. A lot of these are a little more complicated than we want to get into in this episode, but they'll definitely have a place in future episodes. But metal recycling is another really important type of recycling. It's also one that has its own challenges. So one of the really big problems, and something that really relates to this, the idea of the holidays and people getting gifts that might eventually end up in landfills or end up in recycling, is that a lot of electronic components are comprised of many different metals. It's not always just aluminum. It's not always just steel. And so that becomes a problem because if you can't separate these into their separate sortable components, then it's not easy to actually process them appropriately, and then you end up getting metal that's impure and not useful for later applications. And another challenge is that the lifetime of metal products can span many years before they actually have to be recycled. Think about a lot of phones are made out of metal these days, and the components in there are pretty useful for making new phones. There are a number of companies that do recycling there, but there's a lot of different metals in there, and so if you want to try to recycle a piece of metal to be used in the circuit board, for instance, you probably want high purity because contaminants are going to lower your
separation process. We'll talk about it later, but it's tricky. It's tricky to separate different things.
It's going to lower your performance, and so it's not as economical. It's going to cost a lot more money to try and actually recycle that.
Something I learned in this episode is that when you think about recycling, the whole idea is you take something that's waste and you use it again, and you can maybe even make money doing this. I mean, as a kid, I remember collecting aluminum cans. I don't know if you did, but when I was a kid, me and my brother did this all the time. We'd collect massive amounts of pop cans, and we would take them to the recycling place, and you'd get some money out of them. Right now, you can do it with glass bottles. In California, it's like 10 cents a bottle or whatever they are, right? So you could think about making money on them. But in looking into studying this episode, most materials you're not making money on them. There's some exceptions. Aluminum's a good exception. If you look at making aluminum into products, if you were to mine it out of the earth, you have to go through typically the Bayer process is how they get aluminum, which is complicated. There's this heating step. You have to add a base to get rid of the silica. Then there's it's this whole process. You turn it into aluminum hydroxide crystal, and then you have to heat it to burn off the hydroxide, and that ends up with the aluminum oxide. It's very energy intensive. They use a ton of energy. For example, it's 186 megajoules per kilogram if you do it from this bauxite ore, whereas if you go from secondary sources, it's 10 to 20. So this is an order of magnitude less. So there's some real advantages there, and it actually becomes economically viable to recycle some things like aluminum.
Mm-hmm. And so that's really the motivation that's kind of driving why you'd want to actually pursue the recycling route as opposed to mining new materials. But now if you're going to go that route, you have to face those challenges that we talked about.
And of course, this depends on where you're at. If you're in New Jersey, where homes and cities are crammed together and there's not a lot of empty space, then a landfill to throw your waste out is going to cost more money. So recycling might have better economics there because disposing of waste might be more expensive. Out here in Salt Lake City, where we've got big empty deserts around us, it's pretty easy for them to find empty space for landfills, and so recycling is a little bit less economical. I'll say this, though. Everything changed in the year 2018, right? We had 2 decades essentially from 2000 until now where our recycling, composting, all those numbers were essentially flatlined. Things weren't changing. And now everything is changing because in 2018, China decided that they no longer want our junk. And who can blame them, right? China in the past really needed raw materials. So sending them plastics and papers, mixed papers for recycling, all these different things, they could turn those into useful products and they had an appetite for it. But they are moving away from that because of the environmental impact it has for them to do this recycling. The biggest issue that they have is that when we send them our single stream recycling is that there's these impurities. You mentioned that they can be up to 15%. Other studies show that we're typically between 4% and 25% with our impurities, right? China in 2018 said we're not going to accept recycling goods until the impurities are down to 0.5%. That's crazy. That's really low. That's so low that the municipal recycling facilities, they can't do that at low cost and stay in business. And so what you're seeing is that you used to have municipal places who would bundle these things. They bundle them into giant 1-ton cubes. So basically like a cubic meter of garbage that gets smashed together. They used to be able to sell these things and make a profit on it. And now no one's buying. And so they're trying to send them to other countries. There's been a move to send them to other countries, for example, Vietnam, but they couldn't keep up with them. And they've actually closed their ports because they couldn't keep up with the volume of recycled goods. So what you're seeing is there's a huge backlog. You can see lots of news articles about this where municipalities used to be able to get rid of these every couple of days. They'd clear out their stock of recycled goods. Now they're piling up. And eventually they're going to have to get rid of them if they don't have space to store them on site. They actually went from having a product they could sell to going to something that they have to pay to get rid of. And obviously that's just going to kill the economics of recycling in a lot of places. And you're seeing a need more now than ever for innovative ways to get rid of these impurities.
Mm-hmm. Yeah, they accepted about 40% of our recycled waste beforehand.
Man, that is huge, 40%. And now that's staying here, and it's staying on site for many of these places, or they're just throwing it away. So consumers who are, consuming these goods and they think that they're recycling them, they send them to a municipal recycling center, and many times it's just getting thrown away after all, which is tragic, right? Something I found interesting is that in the United States, there has not been a recycling plant built since 2003. For the last 2 decades, we've just been like, hey, this is a pretty sweet gig we've got going. We send our crap to China and they just recycle it for us. We all feel good about it, but we're going to have to get creative because that old approach isn't going to work.
So this is definitely going to drive a lot of demand. We're going to need to come up with new processes and potentially new materials to enable better recycling in the U.S., especially with how pressing environmental concerns are recently. And so, how are companies actually going about this? What are engineers doing to try and tackle this problem and make it economical? Because at the end of the day, we can make all these very advanced recyclable materials. We can make all these very advanced processes for doing that, but the economics are ultimately what drive it. And so how do we do that?
Well, one easy way to separate materials is with magnetics, right? Anybody who's seen like a waste line, it's been in like cartoons and shows since forever. You've got the waste trash going in. If you want to separate the ferrous metals from the non-ferrous ones, we have a pretty slick way. We can use electromagnets and we can just grab it right off the conveyor belt. How does this all work, Andrew? You want to give us an overview of the basics of magnetism?
Sure. So on an atomic level, there's two sort of ways that magnetism or magnetic moments come about. The first is that, as electrons, they have a charge, and as they are spinning around the nucleus, we learn this from physics too, that a spinning charge will generate an electric field, and that electric field also generates a magnetic field. And so we can derive some magnetism that way from the orbiting of electrons. But the other way that we can do this is we can define the atoms of elements in terms of their quantum numbers. These are NL, ML, and MS. These are usually taught in your chemistry class. This quantum number MS is referring to electron spin. Now, they're not actually spinning, despite the name. You can kind of think about this as them trying their hardest on the inside, but nothing's actually showing on the outside. And this highly depressing and relatable force is what contributes to magnetism on a quantum level, and as you get enough of this, you then can scale that up and get magnetism on a much larger level. So these spins or orbiting electrons will manifest themselves as magnetic moments, and these moments will typically point in random directions. For every atom you have a moment, and so think about how many atoms you have within a material. That's how many moments you're going to have. It's going to be hard to get any sort of net effect out of this. But these moments can actually be aligned, either spontaneously or via an applied field. And so when they are aligned, then you get this strong net magnetic field that I think a lot of us are used to. So I guess the question is, can all metals be magnetized? And yes and no. So there's three main categories of magnets. There are metals that exhibit diamagnetism, metals that exhibit paramagnetism, and then ferromagnetism. So diamagnetism, this is something that appears in all metals, and this is the tendency of a material to oppose an applied magnetic field, essentially be repelled by that magnetic field. So going back, looking at an atomic level, in the presence of a magnetic field, electrons are going to want to exert a force that runs equal and opposite to what is being applied to it. And so their orbiting will be accelerated such that they can essentially affect and repel this magnetic field, and you can induce essentially a magnetic moment within the material when it's under the influence of this applied field. And in this case, the magnetization is pretty much limited to just the electron's orbital motions.
So if you've ever seen the YouTube video of the frog levitating in the it looks like an MRI machine in the magnetic field, this is an effective diamagnetism. We'll put a link in the show notes. It's pretty cool worth watching. And it's not like the frog is made of ferrous metals. This is a diamagnetism at work. But yeah, a frog is sort of floating through the air. So we'll put a link to it.
So next, you get to paramagnetism. And this will, if a material exhibits paramagnetism, remember all materials exhibit diamagnetism, but paramagnetism will dominate and will be the sort of defining feature of this material. In these materials, you have unpaired electrons, so that is orbitals within atoms that only have one electron in them, which means that their spin is not canceled out by a neighbor. And so, as a result, free electrons, these magnetic moments, can be aligned in such a way by a magnetic field. And so, if you place it in a magnetic field, you're going to see the same effect that we saw with diamagnetism, but when you remove the field for a brief amount of time, you will have all of your magnetic moments, and you'll see a bulk net magnetic field within your material. So finally, we get to the ones that I think most people are familiar with, and that is ferromagnets. So materials that exhibit ferromagnetism have unpaired electrons, just like paramagnetic materials, but what they also have is this tendency for these magnetic moments to orient parallel to one another in the absence of an applied field. So what this means is that these magnetic moments will actually align themselves spontaneously. And what you end up getting are these, essentially the creation of these magnetic domains where you'll get lots of areas, almost like grains in a material, where all of the magnetic moments of atoms will be aligned. And if these domains get too big, then they'll start to split and form other ones, and you'll kind of see almost like brickwork, if you can imagine that, of different orientations of magnetic moments. But these can be aligned to through the application of a magnetic field or via spontaneously in such a way that you can create a permanent magnet. And that's what makes these really special. But not all materials can do this. As you probably noticed, aluminum is not magnetic naturally. And so the ones that you're probably familiar with are iron, nickel, cobalt. They're alloys, as well as some other rare earth metals such as neodymium. And so these are the materials that retain that magnetic field.
Maybe one other thing I would add on to that is that you have ferromagnetism when all these domains are lined up with one another. If they're all pointing the same direction within the domain, then you get the magnetic field. But you can also have them pointing opposite directions, but one is larger than the other. So if you've got like 3 magnetic moments pointing one way and then 1.5 pointing the opposite way, there's still a net magnetic moment. And so we call these ferrimagnets. And there's also something called AntiFerromagnetism, where let's say you've got a magnetic moment of 2 pointing one way and 2 pointing the other way. So this thing is still aligned. It's not paramagnetic, but it aligns in such a way that there's no net magnetism. So it's an antiferromagnet. So it's not going to be able to be useful for separation, right? It's not going to have a magnetic field that will exert the magnetic force when you apply electromagnet to it, for example. So with recycling, with that knowledge about basics of magnetism, we can start thinking about clever ways to do separation. If impurities are the biggest problem with modern-day recycling, then separation is the answer. It's king, right? And there's different ways that you can separate recycling. There's flotation, right? Anybody who's panned for gold basically knows how this works. If you have different materials that weigh different amounts in terms of density, you can either do that in fluids of lots of different varieties, and there's lots of different varieties, but the main idea is that heavier particles or objects will sink down lower, lighter ones will be up top, so you can separate them in that way. There's things that you can do by melting, where you literally heat things up, and as they melt at different temperatures, you could think about the slag floating to the top and you could separations. For example, when we talked about our steelmaking episode, the very first episode of this podcast, we talked about that a fair bit as a way to remove carbon from steel. There's settling, which is just like the opposite of flotation. There's the magnetism approach, which we mentioned earlier, where you apply an electromagnet and it's going to pull out ferrous metals and things like that. But there are other innovative things that we can do. We're going to take a quick break, and when we come back, we're going to chat with Dr. James Nagel of EDX Magnetics. This is an innovative startup company that's commercializing the separation of metals with a totally new approach. The Materialism podcast is sponsored by MattMatch. Now, if you've heard us talk about MattMatch before, then you know that it's a really great resource for connecting engineers who are designing products with the people who sell the materials that will go into those products. If you need just the right aluminum alloy for something, you can look up all the different providers, look up their properties, and compare them. Well, this week, we want to show you a new tool that MattMatch offers. If you go to mattmatch.com, you'll notice that you can type in properties or types of materials in the search bar, but just below the search bar, you also see the search by application box. If you collect the search by application box, what it pulls up is a bunch of different industries. There's 41 of them that they have listed, things like environmental health and safety, energy, food industry, defense, cutting tools, and so on. On any of these, if you click on it, what pulls up is a series of subcategories. So for example, I just clicked on packaging, and below that, I see things like containers, food packaging, packaging material, sacks, spools. On any one of those, if I click it, what I will see is many of the common materials which would be useful for these applications. For example, under packaging and then packaging materials, I see lots of different plastics which are going to be used for materials. And if you also click on this, there's 3 different articles that MattMatch has written. These are written in a way to help bring users up to speed on the breadth and the different types of materials available for a given industry. You might have thought that aluminum was the only way to go about picking material for this, and the articles might introduce you to ideas that you hadn't even considered about in terms of other materials. So I think this is a useful resource for people that are just moving into a new industry and they don't even know what materials they should be searching for.
And best of all, this service is completely free to use.
Yeah, it's a great resource that I constantly find myself wishing I had known about when I was an engineering student. So check it out, MattMatch.com, and see if they can help you find the materials that you need for your next application. Okay, we're back from the break, and to help us understand a little bit more about this big question of what's the best way to separate materials for the recycling process, we've got an expert, Dr. James Nagel, who's going to explain a little bit about how his technology could potentially be transformative in this space. James, you want to tell us a little bit about yourself, who you are, where are you from, what you've been doing?
Yeah, thanks. My background is in electrical engineering, and I actually earned my PhD here at the University of Utah in 2011. And I was brought into the electrodynamic sorting group with the Department of Metallurgical Engineering.
Which is now the Department of Material Science and Engineering, which we are
That is
super
true.
excited to tell people about. We finally merged. Okay, so are you a Utah native originally?
I've lived here for a good 20, 25 years, so I guess that qualifies as native, right?
Fantastic. Okay, so before we dive into how your company works, can you just talk us through give us some context on what does it mean to separate things? Like, where's this happening? Who's buying these things? Where are they selling them? What's the process actually look like?
So most of my exposure has been with automotive shredders, and there are about 300 or so of them around the country, and usually see a major shredder anywhere near some kind of major metropolitan area like Salt Lake City or New York City, that sort of thing. And these are different from your local municipal garbage and recycling plants. But any one of these shredder facilities, if you go to YouTube and look up automotive shredders, you actually see these things. There's apparently some little subculture on YouTube where people will take one of these shredders and they just throw like
Everything.
couches into it and chairs. And
I'm picturing like the brave little toaster, like this cartoon. Does it look anything like that, or is this like not the case?
It's basically that. But they're basically designed to just shred anything about the size of a car and below.
So they don't have to chop the car up ahead of time. They smash it and just like drop it right in?
Well, usually they'll pick apart some of the more valuable stuff, like maybe the rims or a catalytic converter might have some platinum in it and that sort of thing. But then the rest of the car is just dumped into one of these shredders for
So why on
kind
earth
of a
are they
size
shredding
reduction.
it? That sounds hard and complicated. Like, why are you shredding it?
It makes separation of all the materials much easier. And it's also good for size reduction as well, a big part of that. It's easier to deal in just raw shredded chunks of material than blocks of carburetors and engine blocks and tires and things like that.
So what types of metals are present in a car that you actually go about separating?
So any given automobile will primarily have a lot of steel in it, of course, for things like the frame. The engine blocks and the carburetors and that kind of stuff will have lots of aluminum, which has actually been a big shift in the last couple of decades.
Yeah, for lightweighting?
Yes, for the light weighting. So I guess back in the old days, presumably your engine block was made out of steel, which is heavy. And ever since the 80s or 90s or so, they've been making a lot of the car parts out of aluminum, which is incidentally why you've seen a lot of your fuel economy going up in the last few decades.
What about other metals?
There's a little bit of copper, zinc and brass, but it's not just cars that gets in there. It's refrigerators and couches and whatever is left over from demolishing a building, say. A lot of this stuff finds its way into these shredding facilities.
Okay. So at the bottom of the shredder, you have some big pile of shredded up metal and other things. What's the next step?
So usually now you have this mixed bundle of material that has to be separated in some way. You can't just recycle that directly, right? So usually what happens is the first step is magnetic separation. That's by far the easiest process there is. And it's just a spinning little array of magnets going over a conveyor belt that pulls out all of the ferrous material like iron and steel. And that, incidentally, up here, if you go north to Plymouth, Utah, they have one of these facilities, and it's a recycling facility and next to a steel mill. So all of the steel they get out of the cars just goes immediately to train cars right off to the steel mill. But once you get all the magnetic material out, what's left over is this mixture of non-ferrous metal and non-metallic fluff is the word for it. So fluff will usually refer to things like
Seat cushions.
your seat cushions and the tires, right? Plastics and that kind of material.
How do they separate those?
So the next step, if you want to get the metal out of the non-metal, the most common way that we've seen is eddy current separation.
Okay. So why don't you describe that? Because that's what your technology centers around, is
Yes.
eddy current separation. Can you give us a really simple description of how that technology works?
Well, the most common embodiment of an eddy current separator is a cylindrical array of permanent magnets. And you just spin it really, really, really fast, you typically say 3,000 RPM, and you move material over it on a conveyor belt.
So I'm picturing like a bread pin, and I've like super glued permanent magnets to this thing,
Uh-huh.
right? So the rolling pin can roll, and on top of that, I've got a conveyor belt with materials up on top of that.
Yes.
Am I getting something wrong?
That's exactly
That's
it.
the main idea. Okay. So how does that do any separating?
So when a piece of metal goes over it, you have this time-varying magnetic field exciting that metal.
So the rolling pin has magnets, but because it's rotating, the field is changing.
Yes.
Okay.
So the key is that you can't have a static field. It has to be changing in some way or moving. And if you've ever taken second semester physics, you'll know all about Faraday's law of electromagnetic induction. So that changing magnetic field causes electrical currents to flow around in the metallic particles. And then that current in turn reacts to the magnetic field itself. It's the Lorentz force law, if you're familiar with that. And it creates a repulsive force that pushes the little bits of metal up and away from the field.
So your plastics and the other fluff, the tires, things that don't conduct electricity, as they move through the changing magnetic field, there's no current induced in those materials. Therefore, there's no magnetic field to be repulsed. So they just continue on the conveyor belt.
That's correct. They're insulators, so no electrical current can flow, and so there's just nothing to react with the magnetic field, and they just drop down immediately.
But the metals, these things, they interact with the magnetic field from the rotating thing, and you said, are repulsed. So they're going to, fly through the air?
Yes, they actually will physically jump up and away from the field, and so you just put a little mechanical divider between the two trajectories. So the metallic stuff will jump up and over the divider. The non-metallic stuff just drops under the other side.
That is so
And
cool.
with this process, are you able to screen for different types of metals? So for instance, could you make one type of metal, say aluminum, jump higher than, say, copper to get even further separation?
With a traditional embodiment, the answer is not really. It's mostly just gets metal out of non-metal, and that's the best they can do with the mechanical embodiment. In principle, however, if you had a very high frequency magnet or a very strong enough magnetic field, there are ways to get around that.
So is that how your technology differs from maybe something else that you could buy today for eddy current separation? Is the ability to do this additional separation?
Yes, so our technology is essentially the same principle, but instead of that rotating mechanical array of permanent magnets, just imagine taking that whole assembly out and replacing it with electromagnets.
Ah, okay.
So that changing magnetic field is not created by mechanical motion, but we're
an alternating
exciting
field.
it with an alternating electrical current. So in that embodiment, we can easily get frequencies that are 10, 50 times greater than what you would get out of a mechanical array.
So what advantages or disadvantages? Obviously, you can change the frequency. So now maybe you could separate different types of metals. What other advantages or disadvantages are there? Does yours use more power or anything?
So there's a lot of amazing advantages to that. The first advantage is obviously the high frequency for a number of reasons. First, as you go higher and higher in frequency, you can induce current into smaller and smaller particles. So there's kind of this size and geometry component that goes into the eddy current separation. So that is to say, not all particles will jump equally well based purely on just how big they are or their overall geometry, say.
So, for example, you could still be separating just aluminum, but now you could be separating small versus large particles. So this could be a sizer?
It's more like the mechanical embodiment is good at getting metal from non-metal, but it has kind of a lower limit to the size at which it will extract metal.
It won't catch small particles.
It won't
for
catch
example.
smaller stuff.
Gotcha.
And there's actually specialized embodiments of eddy current separators where they go out of their way to just increase the frequency as much as they can and spin these things as fast as they can and get them as close to those particles as they can, just to go after the smaller or fine-sized particles, as they say.
What about lifetime of the tool? I imagine if you're spinning anything, things just wear out mechanically. If
Yes.
you have fewer moving parts, do you get better lifetimes on your tool?
Yeah, so that absence of mechanical rotation means there's a lot less friction and a giant moving part is now removed out of your system, which means it, in principle, should be much more reliable in the long run.
And what's typically the cost difference between, having a mechanical spinning component versus an electromagnet?
That's kind of a hard question to answer because it's more of a question of the established technology that's been around for decades versus a fresh new embodiment that hasn't had all of the bugs kinked out or doesn't have that huge infrastructure, that huge foundation of infrastructure to manufacture it on a large scale.
So tell us how this company got its start, and then how did you get involved in it?
So initially, this project was funded by the Department of Energy under ARPA-E, and it was a big project with metallurgical engineering, and they wanted to figure out ways to separate metals. And we worked on this project for a good 4 or 5, 6 years, and eventually we were encouraged strongly by the Department of Energy to create a spin-off because there was a real need in the recycling industry for this sort of technology. So another key advantage of the high frequency is that you can separate non-ferrous metals from other non-ferrous metals. In particular, as you go very, very high in frequency, the forces acting on the particles all saturate to kind of a consistent value. So what that means is light materials like aluminum will accelerate up and away from the magnetic field far more dramatically than heavy stuff. So in a sense, what you get is kind of a density separation.
Yeah, it's a density separation made possible by the eddy current.
Yes.
High frequency. Oh, that is really cool because they all experience the same force. So now it's just a matter of how heavy they are to get the lift.
Yes. So you can't do that with a mechanical embodiment because the frequencies are limited to about 1 kilohertz or so.
Oh, that's cool.
When you go up to say 10 or 20 kilohertz, now all of a sudden the forces acting on all the metals are the same, and so now you essentially get different accelerations of your material based on the density. So what our machine can do is actually extract aluminum out of the non-ferrous composition.
So I'm picturing a pile of scrap going in, and you've got your device set up for, say, one frequency, so you could separate one thing from another. Now that scrap would get run through again, but you've changed the frequency, and you could do additional separations to make it more and more pure in terms of your end product?
Sort of. So what happens is, ideally you want to get as high as frequency as you can. The only real trade-off is that for when you pick a frequency, you have a lower limit to the particle sizes that you can get out of it. So the only reason why you would have multiple stages is you would say, okay, this particular machine is going to go after material that's, say, 5 to 25 millimeters. And then you'd have a separate machine to process the remaining material, and it would have, say, 50 kilohertz instead of 10, and then you would be going after the 2 to 5 millimeter bits in that kind of embodiment. So the high frequency means you can separate non-ferrous from other non-ferrous, but you also have to deal with that size component at the end of the day. So it's complicated. There's not really simple answers to a lot of this stuff.
Yeah, that's what I was going to ask about. I think you just answered it, though. Like, how do, they're going to have different weights based on their densities, but they're also going to have different weights based on their sizes. So I imagine that poses another challenge as well.
Yeah, so the geometry of your material plays a huge role in how well you can separate it. So a great example is, say, copper. All right, well, let's look at it like from just what happens when you shred, say, an engine block. You get these nice little chunks of aluminum nuggets. But what you'll also see, the copper will be stringy stuff, usually like in copper wire.
Probably.
So that geometry component can actually work for you in your separation process because it's not just the density, it's just the nature of the material itself and how it interacts with that field.
So have you guys published benchmark sort of, are you the best in the business right now? Like, how do you quantify this? Like, are you given a mixed lot of materials where the actual composition is known and you're supposed to sort it? Or how does this actually get tested scientifically?
So what will happen is we just approach a scrapyard and say, give us your material right now and what's giving you the most trouble, and we'll see what we can do with it. And usually they give us what's called Zorba. And that's usually what happens when you shred automobiles. It's a composition of metal that's primarily aluminum, but will usually have a little bit of copper and zinc and brass in it as well.
And those typically would not be easily separated.
Right. Usually it used to be that stuff would just go straight to China, or they would just kind of sell it to a smelter as is for less than it's worth.
I see. So who would buy your tool? Is it these scrap lots? Is that would be your target customer?
Yes. The automotive shredders are the people who would be a very good market for this technology because they're the ones who are shredding the cars and doing everything they can to break up the material, and ultimately they would like to just sell directly to a smelter for the most value of a pure product.
And would the market be primarily U.S. based, or is this global? Would you be selling them all over the place?
Anybody that has shredded automobiles would be able to benefit from this sort of technology, which is basically all around the world in the industrialized world.
And what about applications in consumer waste? Obviously cars are going to be a much better application due to the variety of metals that are going to be present in there, but does this also see a lot of benefits in consumer waste, or do the benefits kind of lag behind?
Consumer waste, in principle it could, but it's just kind of an issue of the scale of what consumer waste processes. You don't really see a lot of like metal, aluminum, and copper in consumer waste. There's a lot of, say, plastic and food waste that goes into there. But you do see things like aluminum cans, which is why they will have eddy current separators already in some facilities. But really, the majority of the metal processing is in these shredder facilities who deal with cars and refrigerators and that kind of stuff. Anything that just is dense with metal usually does not just get thrown away in a dumpster and sent to your local trash yard. It usually goes to a scrap yard.
I'm curious, what's the rate at which you can actually sort? I assume there's like a kilograms per hour or something like that measurement. What is your rate, and then how does that compare with traditional eddy current separators?
So the embodiment of our machine is basically exactly the same as a traditional eddy current separator. All we've done is replace the magnet with the electromagnet.
Okay.
So, for example, a 18-inch machine that we have. So it's an 18-inch magnet with material flowing over the top, and that can do about a ton an hour very comfortably.
A ton an hour.
And there's not really a hard cutoff to this stuff either. It's more of what's your comfort zone, because you can always just shove more material through the thing.
But your impurity changes, right? I'm sure.
Your ability to separate it more, because there's just more
Yeah.
chaos and collisions in your sorter as you push it.
Okay. So a question I've still got is, will this be as transformative as I hope it's going to be, right? Will this change the recycling paradigm? Will this change the issues that we're seeing right now with recycling at a turning point, I think, in some ways, at this country? What do you think?
So that's a hard question to answer, because if you had asked me 3 years ago, the answer would have definitely been yes. We had scrap yards from around the country practically beating down our door, asking us when they can be the first to buy our machine. And now the market has completely tanked on metal recycling.
What caused that?
It's hard to say. A big part of it is an inability to export material to China like we used to. That was a major part of it. There's just a glut of aluminum, as far as I've been told. That's not really a question I'm the best person to answer, though. There's more marketing-focused people who can tell you more about the commodities and the saturation going on. The best answer I can say is we have talked to a lot of scrap yards, and a lot of them have just said we can't even sell aluminum now, even if we wanted to. That's why they're stockpiling it or just burying it, or they're shutting down their shredders entirely.
So what does the future hold for this? This is kind of a grim picture you're painting. Do you think that it's cyclical and it will rebound, and at some point this will not be the case, or what's your outlook?
It is probably cyclical. A lot of this might rebound if things improve, say, with China. A lot of it could rebound if better trade relations are established with other countries like, say, India or Indonesia, other countries that are just hungry for metal. It's just a matter of, I guess, establishing those relationships, but I'm really not the best person to answer that kind of a question.
What about the environmental component? Will there come a time when they say, all right, this is going to be more expensive, but if we start including the ecological impact of traditional approaches, whether that's energy consumption or pollution, do you think that would eventually drive it towards using more secondary recycled goods?
One of the main problems right now is that it's just so cheap to produce aluminum from primary feedstock, and aluminum is one of the more abundant elements in Earth's crust too. So your main competition right now is not really other recycling processes. It's just raw mining in general. And as long as energy itself is cheap, then it's very difficult to recycle the material rather than just create more of it from virgin material.
It's a bit of a bummer.
Yeah. So it's this strange paradox where the Department of Energy would really like to see recycling more prolific because it creates less strain on the electrical infrastructure. But at the same time, energy itself is just so cheap that that's your main competition right now.
Yeah,
but you could also say a big part of it is just there's a fixed number of smelters in the United States, and there are, I guess you could say, institutional hurdles towards opening new smelters to create or to increase capacity. So there are other barriers in that kind of sense. But that's kind of how the aluminum market is panning out right now, is we'd like to really recycle this stuff, but energy itself is just so cheap that it's very difficult to get into that market. But if demand were to go up, we would probably see that market return, and our ability to sell machines would come back.
Rid of them.
It is really interesting to see that many of these challenges that we're facing go beyond just making better materials or better technologies. There has to be enough infrastructure in place to allow those technologies to flourish.
So that is something I've been told a little bit, is the infrastructure, that there's just a fixed number of smelters in the United States, and if they're just flooded with material,
they don't need to buy your stuff, because yours is going to be a little more expensive because the separation costs a little bit.
Mm-hmm. Well, it's not just that it's more expensive, it's that there's a glut. The market is just completely flooded with scrap.
Yeah.
And so one anecdote I've been told is that it's just 9 months to get an appointment to even settle on a price to sell your material to them.
Okay, so thanks for joining us for this episode. As always, if you have questions or feedback, we would love to hear you. So send us an email. You can send us an email at materialism.podcast@gmail.com. We'd love it if you would subscribe to our show and give it a rating. That helps other people find it so that more people can realize that there's a good materialism podcast out there. Finally, check out our Instagram page. We are at materialism.podcast. You can connect with us there. You can tell us what sort of episodes you'd like to hear from in the future. If we get something wrong, you can let us know. And we always want to give a shout out to the people that allow us to have great music on the show. That's Alphabot and Kolobite. We appreciate them putting together tracks and making them available for us. You should check them out. Alphabot is on Spotify, and Kolobite can be found on kolobite.bandcamp.com. Until next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.